titled Transformative Particle Enhancing Active Cooling Control System Without Pumping Penalty.
Well, good morning, everybody, and thank you very much for the opportunity to speak to this audience. First time that I participate in one of the TFAWS meetings, and I'm very excited about it. My name is José Lage, and we pronounce José because I'm originally from Brazil, so we speak Portuguese. But having lived in Texas for over 30 years, I got used to be called José a lot, so I answer to that as well. So today I'm going to share with you some results that you got on particle-enhanced active cooling control system without pumping penalty. And of course, the catchy wording here, pumping penalty or phrase, is the attention that I want you guys to focus on. I am a professor of mechanical engineering at Southern Methodist University in Dallas, Texas. And one of my students, Amir Kiai, who graduated a few years ago, is now working at Applied Materials in California. He's a co-author of this work. All right. Okay. Of course, every time you build a convection-based heat transfer system that involves channels, the main concern is the formation of boundary layers. Here's just a sketch, a very simplified sketch of what one can find, either having a regular pipe, or regular diameter, or parallel plates. It doesn't really matter what geometry you use. The fact of the matter is, no matter also what kind of flow distribution you have at the inlet of your channel or heated section of your channel, let's say, you are going to have boundary layers developed along the surfaces of your channel. And it's exactly at the surfaces where your heat transfer is going to take place between the walls of your pipe or the external section of your system and the fluid that's flowing through your pipe, either to cool the walls of your channel or to heat the walls of your channel. Our main concern, as I mentioned, then the growth of boundary layer or the existence of the boundary layer, better saying, is more general, results in a problem at the interface fluid solid, which is shown in here. And that's exactly the decrease in speed that you have at that interface. And of course, this is the hydrodynamic part. You also have a thermal part. Nevertheless, the existence or growth of boundary layer is a hindrance or impinges a hindrance in your heat transfer capability. And that's something that heat transfer engineers have spent decades trying to minimize or even to resolve. Showing this sketch, we have usually, if you consider a uniform inlet profile, you have what we call hydrodynamic entrance length, entrance region, to achieve fully developed velocity profile. And from that point on, the velocity doesn't change anymore, assuming this is a regular channel with a uniform velocity. And we can even, excuse me, predict the entrance length through this formula. We know basically everything that one can wish to know for this class of problems. So our concern then is really how to minimize the effect of the boundary layers that you have near the solid fluid interface. In terms of heat transfer enhancement strategies, the main idea is essentially to break the boundary layers or to induce a better mixing of the fluid flowing in the channel. And there are several modifications that have been proposed in the past several years. Some of them involve geometry modifications, either putting fins, turbulators, oscillators, winglets, wall roughness, you name it. Whatever you can do in your system to disturb the flow, to disturb the boundary layer, usually leads to a better heat transfer capability. There are also alternatives in terms of adding surfactants to the liquid or fluid that you have, in this case, the liquid, and then using nanoparticles. And Professor Dukan just gave us a talk about it, so that was a very good introduction for my talk. Here on the left, we have a few pictures, like, for instance, if you have a channel with some protruding blocks, and these are heated. Let's say this is a electronic board, and you want to cool it. One of the ideas that people had, well, put an oscillating plate right in the middle. So you have some mechanical activation system in here to make this plate go up and down, oscillate in time. And by doing so, it forces a change, transfers this oscillation to the flow, and hopefully that will help with your breaking of the boundary layer. Here on this 5 sketches that we have, flow along a channel, The top one is just your regular flow. You come in with a cold fluid, regular velocity, and then you see the development. You have, again, hydrodynamic and thermal development, and things that can be done to enhance that. If you just put a plate right at the entrance, you force a distortion of the boundary layer. If the plate oscillates, you can even enhance the disturbance downstream. You have this formation of eddies, and these eddies then help bathe the surface of your channel, enhance your heat transfer process. You can use cylinders, spheres, place in your flow, and so on and so forth. All of these strategies have a few drawbacks that are common to all of them. The first one, which is the most important one for heat transfer design, is the pumping penalty. Fine, you can do things that will enhance your heat transfer effectiveness of your system, but you end up paying more in terms of energy to get the fluid flowing, because these strategies, they normally impart on a flow resistance. That means you enhance your pressure drop in the channel. That means you need a bigger pump or more energy in your pump to maintain the fluid flowing. Another one is limited propagation. In a situation such as the creation of vortices, for instance, these vortices, they tend to die out. So if your channel, depending on the length of the channel, depending on how these disturbances are created, after a certain distance from where they are created, these disturbances, they tend to die out, and your flow then go back to a fully developed state with the boundary layers present, and you go back to where you started. And you also have, in the case of nanoparticles, for instance, you have sedimentation and scaling, and some people have already asked about it. And that is a very important practical problem that we have when you use sedimentation and scaling. Now, with all this in mind, then I present to you what was the idea that I had some time ago. And this idea came by working with physicians. I got involved in a project with some physicians at the Southwestern Medical Center here in Dallas. And the problem that they had nothing to do with heat transfer. In fact, they were interested in the gas exchange in the lungs, particularly in the alveolar region. And here's a picture of a fixed lung. This is a dog lung, similar to a human lung, in the alveolar region. So what we're looking in here is what we call the alveolar, which is essentially a wall. It's not really a regular capillary. You have these holes in here that are sort of crosses in the capillary that holds these walls together. And the interesting aspect of this system is that you have essentially two regions. One is the gas region outside, and the other one is the capillary region, which is this tissue in here. Now, the capillary region, if you look at it and see it as a wall, is like a hollow wall in which you have something passing through, and this something is the blood. We have a combination of plasma and red blood cells. As I mentioned, my involvement in this project was really to try to answer some questions that they had with the mass transfer process that takes place at the lungs in the alveolar region. They're particularly interested to know, if we accelerate the blood flow without doing anything else in the structure of the lungs, would that by itself justify the increase in lung capacity that's observed in humans when we exercise? And because there is a lot of another group in medicine that believe, well, no, that's not necessary. Even if you maintain the blood flow exactly the same when you exercise, by enhancing or enlarging the volume of the lung when we breathe air in and out, this expansion will be enough to justify the increase in lung capacity. But when I did this project, of course, I learned a lot about physiology, and that's what the physicians gave to me, and I gave to them my mechanical engineering knowledge. But one thing that caught my attention was the structure of these capillaries, particularly in the alveolar region, which is very easy to see in this picture. You can also see in here, most blood capillaries, they're very small ducts, small channels, and the blood that flows through them, as shown in here, the plasma in the red cells, is such that the red cell size is about the size of the channel that you have available for them to flow. So that is a very particular geometric configuration. And as an engineer that I am, when I look at the system, my first reaction was, what the heck, why would I put red cells in there? I mean, if I am to build a lung, right? If I were the engineer given the task, well, build a system to have, gas exchange so we can use in the human body, why would I use the red cells? Because red cells are, particles. There's an extra entity that you have to care for. in the human body, we know that we have to produce red cells continuously because they kind of get damaged, they die, they don't last very long. So you have all these sorts of practical issues related to the existence of the red cells. So when I asked the physicians, why do we have red cells? Do we really need them? The answer was, today for me it's kind of obvious, at the time it was not, but say, well, we need to have something to protect the oxygen. Particularly, oxygen is very reactive. So if you just allow oxygen to get into the plasma and flow with plasma, which it does, by the way, that oxygen will tend to react to everything else. So when you get to a point in the body near a muscle where you want to deliver this oxygen, you won't have much free oxygen anymore. So you have the red cells with a protein, the hemoglobin, that has high affinity for oxygen. And that's how you make sure that you can transport this oxygen as a free oxygen, let's say, and so that you can deliver where it is needed. Then I said, well, what would be the big deal then to have this protein just floating in plasma? Why do you have the hemoglobin inside the red cell? They couldn't answer that question. Well, in principle, probably it would work if you have a protein that has high affinity for oxygen floating in plasma. When the oxygen gets into the blood, it will get into the hemoglobin, get attached in there, and then the plasma will carry the oxygen for you. So I went back and said, well, okay, if then there is no definite answer about oxygen transportation, that's why you need the red cells. Why do you need the red cells, right? So through the work that I did for them, we did some studies on the effect of blood flow. Of course, we had to include the red cell. And by including the red cell, I consider, well, maybe the red cells are in there not only to transport oxygen, but also to enhance or to facilitate the gas exchange. Because what we have, and this is the problem description and modeling that I'm going to show to you, is essentially a channel like showing in here. And this is just a schematic. And you have fluid, in this case, imagine that's just a liquid or gas, whatever you have in there, that flows into the channel with a certain condition in terms of temperature and velocity. And as the fluid flows into the channel now has a particle that is large enough to flow into the channel, but it gets very close to the walls. So in this system now, I'm looking at the effect of these particles flowing with the fluid in the channel to be heated or cooled. So now I departed from the medical issue, the medical problem of gas exchange in the lower region. Now I'm looking more at a heat exchanger, say it a radiator, very simple one, right? So you have the walls of your piping in this case, I consider having isothermal condition, but you can have any condition that you want. You either want to heat or cool the fluid. And instead of having only the fluid flowing in the channel, you have the fluid with this particle flowing in. Of course, from a fluid mechanics point of view, I know that if you put a particle in a fluid, you're going to distort the flow development, right? You're going to distort the boundary layers. This particle in here, if it is large enough and get close to the walls, it will alter whatever flow distribution you have around this section in here as the particle flows downstream. So the question that I had was, does this affect your transfer process? Does it enhance your transfer process? So to study that, we consider this simple sketch of a channel. We consider a particle placed at a certain distance from the inlet, and a channel with a certain length, a certain size, and we consider the particle to be adiabatic. We consider a uniform velocity and temperature here at the entrance and a uniform temperature at the walls. So if you do modeling for numerical simulation, we consider the fluid as being Newtonian, simple fluid, uniform and constant properties, no viscous dissipation, and we consider the particles being rigid, neutrally buoyant, so the particle kind of floats in the liquid in here, or the fluid that's flowing through. And to simulate what happens in terms of heat transfer, fluid mechanics and heat transfer in this channel, we have to use some balance equations, and here listed are continuity, momentum, Navier-Stokes equation, energy balance. These all apply for the fluid region. And then you have to add an equation for the momentum transport of the particle itself that's considered solid. In this case, this is just Newton's second law. For simulating the process, we use a simplified interaction between the solid particle and the surrounding fluid. We use the one-way FSI. FSI is fluid-solid interaction, in which case the fluid forces are particle external loads, and there's no fluid, there is no solid force feedback to the fluid. So the solid does not interact to the fluid, back to the fluid in terms of imposing forces in the fluid. Of course, the solid is an obstruction for the fluid. The fluid has to pass around the solid, but otherwise you don't have a dual interaction, a back interaction, let's say, a feedback interaction to the fluid. The linear momentum solver was used for the particle itself, considered to be a rigid body, as I said, and that is based on New York integration scheme. So at this point, we are set to start some simulations and see, what happens with your channel when you have the particle in it. For boundary initial conditions, we consider the fluid as being water. So we know everything that we need to know about water when it comes to properties. We consider a channel of about 200 millimeters. The particle was stationary at 12 millimeters in the beginning. And the size of the channels in here, this H is considered to be 4.8 millimeters. And the diameter of particles, we consider 2 millimeters and 4 millimeters. Why did we do that? Well, because we don't know exactly what will be the effect of the particle in the channel. So we decided to say, well, let's just start with a small particle and then increase the diameter and see what is the effect of it. And so we selected these 2 diameters to show some of the results. Again, we consider to have uniform velocity distribution here at the entrance with temperature as well, uniform. And at a certain time, then the temperature of the entire system is 300 Kelvin, which is about 27 centigrades. And imagine that the walls then, the wall temperature is increased to 67 Celsius or 340 Kelvin. Then we considered 5 different cases. Imagine that the fluid comes in here with the velocities 2.5, 5, 10, 17, and 26 millimeters per second. And that gives you a range of Reynolds number between 27 and 280, laminar flow. And we also have here the entrance lengths that were estimated for this system between 6.5 and 67. The numerical simulation for this type of system is not easy, it's very complex. One of the issues we have is we need to have outlet boundary conditions in here. Usually we don't know what is the condition that your system will have at the outlet. We were smart enough to select a long enough channel compared to the entrance length to at least without the particles to guarantee that you have a fully developed flow at the exit, so you can impose the boundary conditions such as listed in here, pressure 0, temperature gradient equal to 0 as well at the exit. Exit boundary conditions is always an Achilles heel for this type of simulations, again, because we are normally unaware of what happens there. And of course, in this system, when you have the particle flowing with the fluid as the particle approaches your exit, you have variations in here. So this boundary condition is no longer going to be realistic. You're imposing something that in reality you want to achieve in practice. So you have to be careful if you're looking at the results in which the particle is very close to the exit of your channel. Here are some results. We have 3 separate sketches. The top one is what we refer to as a clear flow result. Excuse me. Results in which you don't have any particles. Let me guide you through this. Here on the right side are just the time after the beginning of the process, beginning of the flow. So you have time equal to 0. The blue here indicates temperature of 300 Kelvin everywhere, and the entire channel temperature is the same. And then at that time, you jack up the temperature of the walls of the channel to 340. Then you see the development in time of the flow, the convection process, and you see this variation in color near the walls, indicating the development of the heat transfer process that you have. These results are for a inlet velocity of 26 millimeters per second. In here, I know from calculations of fully developed flow, the maximum velocity that you have for the fully developed profile, fully developed flow in the system is 39 millimeters per second, and Reynolds numbers are 380. Then the next set of shots that we have of the flow are shown in here. This shows what happens with the flow when you put a particle that's about 2 millimeters. Now remember, the size of the channel here is 4.8. So 2 millimeter particle is very, very small compared to the size of the channel. And the particle simply is carried by the fluid as the fluid starts flowing, and it goes downstream with a certain development, a certain speed, a certain dislocation. And we can obtain, I'll show you in the next slide how we obtain this. The velocity of the particle in this case is 35.8 millimeters, less than the maximum that you get at fully developed. Keep in mind your particle here is neutrally buoyant, so once placed in the center of the channel, it will remain in the center of the channel. It's a simple simulation. So this indicates that your particle will move at a speed less than the maximum, as you would expect, right? Now, what happens if you increase the size or the diameter of a particle? Well, if you have a particle 4 millimeters, and remember, now you have only about 0.4 millimeters gap on top and bottom of the particle, separating the particle from the walls of the channel, you also see the displacement or the translation of the particle downstream. But in here, it's more obvious that the presence of the particle affects the temperature distribution of the fluid. If you compare this set of slides in here with the top one, you clearly see that the particle has two effects, essentially. One downstream of the particle and the other one upstream of the particle. Upstream, you have the tendency of the particle dragging the cold fluid that's coming in a little bit deeper down the channel. So that should have an effect in the heat transfer process. And the other thing that we notice is this change of colors in here downstream the particle that indicates the fluid in there is heating up. The temperature is higher, is increasing. And that means that your particle is pretty much sweeping or pushing the fluid downstream. And of course, that fluid includes the fluid close to the wall that's heated by the wall. So you're essentially pushing this hot fluid out of your channel. And this, of course, is expected to have an effect in your heat transfer process. This is just how we obtain the velocities of the particle. We have the location with time, so we can plot and get the velocity straight from these lines. We have the two lines in here. The blue one is for the small particle. The orange one is for large particle. And here, this is just an extension of the linear profile. And you can see that in the beginning, the small particle accelerates, and you can clearly see the acceleration of the small particle. And you see that at the same time, this is 2.5 seconds, the small particle is further downstream than the big particle. And this is expected as well, because we know in a fully developed profile, the largest velocity at the center of the channel, the small particle will occupy a region right at the center, so it will tend to move faster than the big particle. These are another results now, just changing the velocity, now using the minimum velocity that we tested, 2.5 millimeters per second, Reynolds number 27. We can see the same effect of the particles. Here is the clear flow variation in time, evolution in time. This is the effect of the small particle, and this is a large particle. We just see the enhancement here of the pumping effect, let's say, or the piston effect of the particle pushing the hot fluid down. You can clearly see how hot the fluid gets ahead of the particle. The rod, remember, is temperature 340, so you're almost in thermal equilibrium with the walls of the particle. So this region here will be a very bad heat transfer region, we assume, because you no longer can transfer heat from the wall to the fluid, because the fluid is now in thermal equilibrium with the wall. But of course, downstream or upstream of the particle, you have that pushing effect or sucking effect of cold fluid, and we need to check what will be the difference between the two. Here I'm just giving you some numerical values of the effect of having the particle. If you don't have any particle, the delta P that you obtain for this channel is 0.232 Pascal. If you have the particle, the delta P increases by only 2.6%. So just make a parenthesis here. I have to make a correction in the paper, because in there we have 1% variation or less than 1%. In fact, it's less than 3%. None of our case is the case that we simulated, at least. We had a pressure increase of over 3%. So there is really indeed no penalty, essentially no pump penalty for having particles flowing with your fluid, because they're essentially sliding in your channels. They just flow there in the liquid or the fluid and slide downstream. These are just three shots comparing velocities, different velocities, velocity variation effect for the largest particle. We expect the largest particle to have the strongest effect in your heat transfer because it's very close to where your boundary layers will be. So you have more effect in the destroying of the boundary layer or modifying your boundary layer. And here we have for different times, because we have different speeds, essentially 2.5 millimeters, 10 millimeters, and 26 millimeters. And you see how different the results are, and hopefully we'll see that also when you look at the heat transfer and effectiveness of having the particle, what is the effect of having different speeds in it. But at least in here, qualitatively, you can see that this low particle pushes a lot of heat and let the heat get really, really hot downstream. And the fast particle, you don't see that effect as much. Here is just a plot at different times for the same particle, 4 millimeters, the large particle, and the highest speed, 26 millimeters per second. And the way to read this graph, you're just plotting what is the heat flux that we have along the entire channel. The channel goes from minus 0.10 to 10. We center our axis here right in the middle of the channel. And you have several distributions or heat flux distribution. It comes from infinite because at the inlet we have a discontinuity in there since you're imposing an inlet temperature that's different from the wall temperature locally, and that gives you an infinite heat flux. But immediately when you go into the channel, the heat flux goes down, and then you have this wiggling in here caused by the particle. And the dashed line in here is the equivalent clear flow result when you don't have any particle. So by comparing these curves, the dashed and the continued lines at different times, you see the effect of having the particle is really this wiggling in your heat flux. So it does have this effect. And when you have the particle a little bit more downstream, and you can see the location of the particle is here, and then a little bit downstream here, and so on, you have this large effect upstream the particle. You have a very large enhancement of the heat transfer coefficient near where the particle is, mostly upstream, and then downstream you have a decrease in the heat flux that you would have without having the particle. So here you have, a conflicting contribution. It seems like the particle enhances the heat flux upstream, but is detrimental to the heat flux downstream. So the question then becomes, what is the net effect? So here we show how we get a quantitative result showing what is the net effect of your particle in terms of heat flux. And we plot here the same distribution that we've seen before for a certain time. This we pick time 2 seconds. Again, dashed line for the clear results, clear flow results, and the continuous line for the particle. So what we do, we just need to focus on the region that is affected by the particle, which is about 8 to 10 diameters upstream and 3-5 diameters downstream. That's the region of influence. And we need to find the difference between the area underneath the dashed line, which will be your heat flux for the clear flow, and the area underneath the particle, which will be then the net effect of the total heat flow for the particle case. We created this figure of merit, which is the difference between heat flux for the entire channel with the particle minus heat flux with no particle, divided by our base case, which is the heat flux without particle. At this particular time, for instance, this result leads to an enhancement of 21%, which is significant. It's only one particle in this entire channel, and we got 21% more heat flux at this particular time. So if you do that for all the cases, for all different velocities, we focus on 4 millimeters because that's the configuration that yields the highest possible heat transfer increase. We observe another interesting result, which is this one in here. For the lowest speed, we actually don't have any enhancement. What we have is a detrimental effect of having particle in the channel, because your heat flux with the particle end up being smaller, of about 15 to 20% smaller than if you don't have any particles in there. So the speed with which the fluid is flowing is important. And here we show that as the speed increases, and we went from 0.0025 to 0.005, and then 0.010, 17, and then 0.026. So these results seem to indicate that there is a maximum for the enhanced heat transfer in your entire channel. This again is the integration for your entire channel, and we got a result which is for 0.010, which is the best result that we could get for this particular configuration, of about 31% increase in your channel heat flow. So this is an important result. We were able, by the way, to plot all these lines in the same graph because we scale the time. This is not the characteristic, the real time of the system in seconds, but it's a scale time in relation to the maximum velocity that we have for each one of these cases. So we could see all the figures in the same graph. Now, looking more closely, why would the particle affect the heat transfer process in the channel? We plotted in here an evolution of the velocity distribution around the particle, upstream and downstream the particle, for the case of 10 millimeters per second, for which your maximum velocity fully developed flow will be 15 meters per second, and the particle diameter of 4. And what we see is right here at the small gap that we have between the particle and the wall of the channel, the maximum velocity that we have here, or the velocity distribution that we have in here, is shows a much higher velocity than the distribution that we had if you didn't have the particle in there. So the particle is then to accelerate the flow at the gap between the particle and the wall. And of course, this flow acceleration will enhance your heat transfer process right there. So now we have this heat transfer process that's enhanced around the particle location. And now we know, at least from a qualitative description, what that is happening.